Hey guys, so today we're going to look at how we can check for language equivalence between two DFAs. So originally we were looking at as in the lesson slide is between two DFAs, but we're going to be looking at how we can check for two languages and check their equivalent. I've kind of made it a bit of a broader title here, talking about checking about if two languages are equivalent, and we're going to see exactly what that means later on, and we're going to see how we can sort of do that check in a logical, systematic sort of way. Yeah, if there's any questions throughout, let me know in the chat, but we're going to begin with this. So the regular expressions below, let's try and write them as a DFA. Does anyone want to come up on stage to talk me through this first one? L equals A. How can you write this as a DFA? No worries. Okay, so I'll talk us through this first one. So we'd just have we'd have an initial node, initial state, sorry. Our language sigma is just AB in this case. We'd have our initial state, and it would go to, we're just accepting A. So we want to make a transition function which just has A on it, and this would go to an accept state. Okay, and then to make it a total DFA, just to be exhaustive, what do we need to do? Yeah, we need to make states for every possible input from every state. So B from the initial state would just go to a reject state, and similarly B from the accept state 2 or A, anything we take in from 2 would go to this reject state 3. So AB from 2, because we only want to accept one single A. We don't want to accept anything else. We don't want to accept something like AB, for example. And then from 3 we'd need an arrow going back to 3. That also just takes an AB. So that means that no matter what we input when we're at 3, we'd always just reject. So BAB, for example, would be rejected. AA would also be rejected because we're only looking for a single A in our language. You could also call this the hell state. So 3 is like a hell state. Once we're there, there's no coming back. We're stuck there, and that recursive arrow, that AB, just kind of keeps us stuck in 3. Into that state here. Okay, let's have a go at the next one. M equals AB. So this time we're concatenating two characters. How could we draw this as a DFA? Does anyone want to come up?
Thank you for having me. Right, so
Awesome.
yeah, so we'd start off with the initial state, call that 1, and
Okay.
that's a reject state, and then we go to state A with a line transition A.
Okay.
Yep, and that's still a reject, and then we do a transition B, and that's the accept, and now we have to make it a complete DFA. So if it starts off with a B, it goes to reject state.
Yep, this would be our hell.
And if we have A followed by A, it goes to that reject state.
Good.
And if we have B followed by anything else, then it goes to the reject state, so A or B. And I think it has A or B coming.
So we need one more thing.
And now we have that loop-de-loop at the going A or B for
awesome.
The hell state.
Yeah, and then we can number our states, and then so yeah, this would be our total DFA for M equals AB, representing this language. Thanks for coming up, Adwit. Yeah, so this would accept the string AB, because it would end on 3. AAB, ABA, BA, all of these would be rejected by this DFA, and so this represents this language M equals AB. Yeah, so we've done L equals A and M equals AB as two DFAs. Let's have a go at another one. So, yeah. Okay, let's have a go at N equals A or B. So, how do we do something like this? We want to represent OR. Does anyone have any suggestions in chat? Any ideas? If anyone wants to come up on stage as well, let me know. Feel free. Okay, I'll just explain something real quick. So what makes a DFA total is when we have transitions defined for every character. This is a partial DFA because we've not defined a transition for A from that first state, for example. To make it a total DFA, we need to define every single character, a transition function for every single character in the alphabet from every single state. And there should only be one such
Hello,
transition
can you hear me?
function defined. Hi. Yeah, I can hear you. Awesome. Right, talk me through
Okay,
this.
so you start off with the obviously starting arrow on a starting state.
Good. Yep.
And then you draw another transition, A comma B,
Yep.
and then yeah, you make an accepting state there. And then you make a held
Cool.
state and arrow A equals, oh sorry, A comma B.
Yeah.
Yeah, just like that.
Okay. Good. Okay. And then what are we missing? We just need this arrow here.
Oh,
so,
yeah,
so this
yeah, I
tells
forgot
us if
about
we're
that,
stuck
yeah.
in hell. Yeah, no worries. Okay, so yeah, this is n equals A or B. Thanks for that. Appreciate that. Okay. So yeah, we can also optionally, like before, we can number our states again, but we don't have to. It just makes it a bit clearer because then we can talk about each state individually. But yeah, so this would accept just A, it would accept just B, but it would reject anything else. So ABA, for example, BA, they'd be rejected because it would go to that hell state. Awesome, so we've represented n equals A or B, the language A or B. Now A star, I'm going to talk us through this one, but it's quite trivial. So A star, we want to accept any number of A's. So how we can achieve this is we can just have A go to an accept state, and then we can have like an A arrow which says any number of A's after that first A would be accepted. Anything, if we take in just a B, that will get rejected. If we take in a B after we take in the A's, that will also get rejected. And then we have this arrow going back to this hell state of A's and B's. So this will accept any number of A's, but it won't accept anything with a B in it. Yeah, so it would accept A, it would accept a bunch of A's. Oh, Victor, you make a good point. So actually, we'll come back to that. But yeah, so we've represented all of these languages, these regular expressions, as a DFA. But yeah, A star actually means 0 or more occurrences. So one thing we'd actually have to fix here is we'd have to make that initial state an accept state, because if there's nothing in the word, that should also be accepted. We could simplify this DFA into something like this. So an accept state which just takes an A, which takes us back to the accept state. As soon as we read in a B, though, we reject and we go to this hell state. I mean, this is a simplified version of rejects. Good job, Victor. So yeah, that's how we'd actually represent this language. Cool. Are there any questions about that? No? Okay. In that case, what we've done is, because we've sort of represented all four of these very, very primitive building blocks, equals A or B, AB, and A star. So we've done or and juxtaposition and just a single character. We can represent any regular expression as a combination of these four, because these four are what make up, these four operations make up any regular expression. And so can anyone tell me what we've sort of proved here? In one way. Yeah, so we've proved Kleene's theorem. Kleene's theorem says for any language L, that's a subset of sigma star, if L is recognized by a regex, then L is also recognizable by a DFA, and vice versa. And we've proved this one way. We've said that anything that's recognized by a regex, we can turn it into a DFA with these building blocks we've sort of made now. Yeah, so that's what we've kind of built up to, and we're going to use this to try and prove that two languages are language equivalent. But before we do that, what does this mean? Okay, so two automaton are language equivalent if they recognize the same language. Before we go into more detail with this, if two automaton are equivalent, then that means the two languages that they represent are also equivalent. We can easily turn these languages into two DFAs and then compare the DFAs. So just to practice turning it into a DFA, let's have a go at this question here. The language P is A or B in brackets star and then followed by AB. So how could we approach something like this? Let's tackle this or part first. Anyone want to come on stage? Or let me know.
Hi again. So you'd start off with that initial state, and you'd have one going to A, comma B, right?
Okay.
And you can have an infinite amount of like now A or B, right? So this one would have a loop back to itself.
Right.
As in like, yeah.
Like that. Okay.
And but that's not an accepting state. And
Right.
then you can have any. You just put like after that you can put A, B, and then the last one's an accepting state, like A.
Yeah, that makes sense.
Yeah.
Only issue we have with that is we have multiple transition functions defined for A now. This is a DFA, a total DFA. So we can't have these two transition functions that take in an A.
That's true. Would you need two separate like branches to go to?
I mean, we could do that, but then it won't be a total DFA. That's the only issue. But I mean, one thing we could. I mean, let's try and think about how we do this as a total DFA. Let's start from the end. So we have an accept state, which we reach by reading a B, and we reach the state there by reading an A. So we kind of need to just reach that state. Okay, and then we have our hell state. So A, B from this accept state would go to hell. A from this state would go to hell, and then B from this state would go to hell.
Yep.
Okay, so we want to reach that state. How could we do this?
Yeah.
Oops. Okay. I mean, we want to kind of put these together. Let's think about maybe how we could do it, but instead of going straight to a total DFA, what could we do? I mean, we could do this as a partial DFA. Let's try and perhaps write this regular expression as a partial DFA, because then what can we do from there? Yeah, because then not a partial DFA, an NFA. Because what can we do with an NFA, a non-deterministic finite automaton? We can determinize it. So
okay, so A from there. Sorry, AB. Sorry.
Yeah.
And then loop and the loop, you know.
Okay.
Yeah, A, B, and now you have the ambiguity here. You put another A coming out of this one.
Yeah. What can we
and
do? Okay, so we're doing an B.
Then
so in the chat, perfect accept state. It's because we're doing an NFA here. We can have multiple transition functions, so we can. This isn't a total DFA. But yeah, so this accepts anything followed by an AB. We know our alphabet's just A and B, so anything followed by an A and B. Let me put this in grey just to make it clear that it's an NFA.
Can we use epsilon?
Whoops.
Can we use epsilon?
I mean, we could use epsilon, but there's no point in this NFA just because we don't need it. It just adds extra steps, but we've done it without, so let's just stick with this one. Yeah.
Mm-hmm.
Okay, so let's try and determinize this. Where do we start? Yeah, let's label the states.
I don't know.
Okay, I'll talk us through it, don't worry. Thanks for coming up on the stage, Adwit. Appreciate it.
Alright, no worry.
Cool. Okay, so we start with our initial state, which is just a set but this is just a single element. It's a singleton. We start at our initial state 1, and then we look at our inputs. So if we take an A, I mean in this case if we take an A or a B, we'll just end up at the set of states which is just 2. Okay, and then we look at 2. So from 2, if we take an A, where do we go? We can get to, where can we get to? From 2 if we take an A. So we can either get to 2 or 3. Yeah, good job. And then from 2, actually yes it is. So from 2, if we take in a B, we can also get to 2 or, oh no, if we take in a B we can just get back to 2. But yeah, if we take in an A we can get to 2 or 3. And let's look at 2, 3. If we take in an A, where can we get to? Yeah, good. Okay, so yeah, we just go back to 2, 3. And if we take in a B, 2, and what other one? 2, 4. Good. Okay. Right. So now from 2, 4, if we take in an A, where can we get to? We're going to look at where we can get to from 2, 4 if we take in an A or if we take in a B. So from 2, 4, taking in an A, we can get to, yeah, we can get to 2 or 3. Good. And then what about if we take in a B? Yeah, we can just get to 2. Okay, so this is our total DFA for this regex. So the idea is, using a combination of what we've looked at, we can represent any regular expression as a DFA. And all we're doing here is we're just kind of, we're proving Kleene's theorem in one way. We're saying any regex, we can use these building blocks we sort of made up in our starter, and we can turn that regex into a DFA. We can represent it as a deterministic finite automaton, as we see here. Are there any questions about that? I mean, okay, so let's test it with these two. A, B. Does it accept it? A, yep. A, and then we take in an A again, and then B. And that goes to an accept state. Good, and that's what we accept, because it ends with AB. Okay, A, B, B, A, it should reject this. A, B, B, A. And we end on a reject state. So it rejects that. Perfect. So we see that it represents this same language. And yeah, so this is just proving Kleene's theorem. For any language L, subset of sigma star, it's recognized by a regex, so we can recognize it by a DFA and vice versa. It's a regular language. Okay, back to language equivalence. Two automaton are language equivalent if they recognize the same language. All this means is they accept the same set of words, the exact same set of words. They accept the same words and they reject the same words. If there's just a single word that one accepts and the other rejects, they're not language equivalent. So this is just the definition of a DFA. I'm sure we're all quite familiar with that. Finite set of states, a single initial state, not multiple, just a single initial state. We have a transition function from every state to another state. So state 7 with input A takes us to state 18. And this is defined for every single state, every single input. A set of accepting states, multiple accepting states. We can have multiple, not just one. And so we can check if two automaton are equivalent by building an automaton that simulates running both of them simultaneously at the same time. And so states within each pair should either be both accepting or both rejecting. Don't worry if that flew over your head. We're going to look into this in more detail. We're going to look at some examples and see exactly how we'd apply this. So let's scroll down. Okay, before we do that, what's the difference between these two? Other than just one's written with curly brackets and one's not. What's the actual difference between what these brackets mean? What is it? Good. Okay, so the one on the left is a set, whereas the one on the right is, as you say, an ordered tuple. Okay, so what does this mean? It means that the actual order of elements doesn't matter in a set, whereas in a tuple, it's implicit that it's ordered, so we didn't need that word ordered, but we'll put it there anyway. In a set, 1, 2 is the same as the set 2, 1. The order doesn't matter. Whereas in an ordered tuple, the tuple 1, 2 is not the same as the tuple 2, 1, because they're a different order. We want to preserve the order in a tuple, whereas in a set we don't need to. So tuples are what we're going to use right now for comparing two DFAs, for running them both at the same time. Sets, we might have seen used determinizing an NFA here, because the order of these different sets don't matter. 2, 3, 3, 2, whatever we put in that set, it would mean the same thing. Whereas ordered tuples preserve order. So we can say the first element represents one automaton state, and the second element represents a state in another automaton. We're going to see exactly how this would work and why the order matters. So yeah, if there's any questions, let me know. Okay, so we have two DFAs here, and we want to check if they're equivalent. So how we start is we look at the initial state of both of them. So let's label the automaton A and B, for example. Let's say the one on the left is A, and the one on the right is B, just so we can talk about them easily. Okay, so in automaton A, the initial state's 1. In B, the initial state is 5. Okay, so let's start with 1, 5. Let's do this in a different color, actually. Okay, now we look at every input from there. If we're taking an input of A, from state 1 in automaton A, where do we go? And from state 5 in B, where do we go? From 1A, we go to 2, and B, from A, from 5, we go to 7. And then we look at B from 1 and 5. B from 1 takes us to 3 in A, and B from 5 takes us to 6 in B. Yeah, so each of these corresponds to a different automaton. The left one is to A, the right one is to B. And then we just repeat this. So you look at where A and B can go from each of the states to each of the other states. Let me know if there's any questions in chat while I'm tracing through this. Okay, finishing off, from 2, 7, an input of A would take us to 4, 9, and an input of B would also take us to 4, 9. Okay, so this is our total DFA, simulating running A and B at the same time. And so now, what we can do to check if they're equivalent is we look at each state. So we look at the accept states in A, in this case it's just 2, and so let's say we underline all of the left side of the tuple that has 2 in it. And then B, we have 7 and 8, so all the right side that has 7 and 8 in it. So left side represents automaton A, whereas we want to remember the right side represents automaton B. So A, this has a 2, that's accept, and that's accept. And then B, 7 and 8. Let's just label the rest as reject, actually. Okay. Yeah, and then 7 and 8. Those two are the accept states, so let's underline all of them. Accept, accept, accept. And then the rest also reject. And so the idea is, these two automaton, they're equivalent because in every single state, these two are matching. They're either both accept or both reject. There's no state where one's accepted and one's rejected. They're all consistent. And so this is how we can prove that these two are language equivalent. Are there any questions about that? Anything anyone's unsure about? Speak now or forever hold your peace. Or just let me know later if you're unsure. Okay, let me save that. Okay, here I've just traced through it myself. It's the same automaton, and yeah, we proved that they're language equivalent. Okay, here's 2 more automaton. I'd like you guys to see if these are language equivalent, and leave what you come up with in the comments. I'm gonna stop the recording here, and the slides are also available in the Discord server. But yeah, I hope you guys found that useful. I'll see you in the next one. Take care.